Welcome back to another video. Here, we will go over the type 1 and 2 errors in hypothesis testing. In an ideal world, we would always reject the null hypothesis when it is false, and we would not reject the null hypothesis when it is indeed true. But there are two other scenarios that are possible, each of which will result in an error. In hypothesis testing, we compare the true state of reality with a decision made based on sample data. This leads to four possible scenarios. Scenario 1 represents a correct decision with the probability of 1 minus alpha. It models the case where we fail to reject the null hypothesis when the null hypothesis is true. Scenario 2 represents a correct decision with a probability of 1 minus beta. It models the case where we reject the null hypothesis when the null hypothesis is false. Scenario 3 represents type 1 error with a probability of alpha. It models the case where we reject the null hypothesis when the null hypothesis is true. And finally, scenario 4 represents type 2 error with a probability of beta. It models the case where we fail to reject the null hypothesis when the alternative hypothesis is true. Let's go over air crew escape example and assume we are conducting a two-sided hypothesis test on the population mean, where the variance is known. Under the null hypothesis, we assume that our sample comes from a normal distribution centered at 50. While theoretically, any value from negative to positive infinity can occur under a normal distribution centered at 50, we define alpha to highlight unlikely values to be observed. For a two-sided test, we push half alpha to each tail, which leads to critical z-values of 1 minus half alpha and half alpha. Due to the symmetry of normal distribution and to make our calculations easier, we replace z of half alpha with a negative value of z of 1 minus half alpha. In the same two-sided test, we can see that under the alternative hypothesis, a second normal distribution is centered at, for example, 52. Our rejection region for the null hypothesis remains anything outside the range of negative to positive values of z of 1 minus half alpha. You can see that the red area under red normal distribution centered at 50 is much smaller than the orange area under the blue normal distribution centered at 52. This means that it's much probable that blue alternative destruction centered at 52 produces this sample. That is why we define alpha, as we realized although it is possible for the null distribution such samples, it is much more likely for the alternative distribution to produce it. The problem is that the blue distribution can also produce sample statistics from negative to positive infinity, and as a result, it can produce sample statistics within the acceptance range of negative to positive values of z of 1 minus half alpha. So, although the alternative distribution is producing the sample statistics, but we cannot reject the null hypothesis as the sample statistic does not fall in the rejection region. And that is why type 2 error accompanies any hypothesis test. In order to measure the type 2 error rate, or beta, we need to measure the area under the alternative distribution, the blue one, that falls within the acceptance range of negative to positive z-values of 1 minus half alpha, as highlighted in blue. There is a trade-off between type 1 and 2 errors. Decreasing alpha, type 1 error, increases beta, type 2 error, and vice versa. If we set a lower alpha, for example 1% instead of 5%, we require stronger evidence to reject the null hypothesis, reducing the chances of a false positive but increasing the risk of false negative. If we set a higher alpha, we are more willing to reject the null hypothesis, which lowers type 2 error but increases the risk of making a false positive conclusion. Although we cannot get rid of type 1 and 2 errors due to their inverse relationship, increasing sample size can reduce both errors because larger samples give more reliable estimates, making it easier to detect true effects while avoiding false alarms. Let's go over an example together. Suppose that an engineer is designing an aircrew escape system that consists of an ejection seat and a rocket motor that powers the seat. The rocket motor contains a propellant, and in order for the ejection seat to function properly, the propellant should have a mean burning rate of 50 centimeters per second and a standard deviation of 0.79. If the burning rate is too low, the ejection seat may not function properly, leading to an unsafe ejection and possible injury of the pilot. Higher burning rates may imply instability in the propellant or an ejection seat that is too powerful, again leading to possible pilot injury. So, the practical engineering question that must be answered is, does the mean burning rate of the propellant equal 50 centimeters per second, or is it some other value? It seems that a two-sided hypothesis test to be appropriate, as any deviations in both directions might be catastrophic. Field experts have advised us to reject the null hypothesis if the sample mean is less than 48.5 or greater than 51.5. In the following videos, we will cover how these number 48.5 and 51.1 are typically chosen. The blue areas represent type 1 error, the probability of rejecting the null hypothesis when it is actually true. Under the null hypothesis, the mean propellant's burning rate follows a normal distribution with a mean of 50. Although possible, we suspect observing such extreme values of less than 48.5 or greater than 51.5 are highly unlikely, and we assume that a different distribution, perhaps centered at 48 or 52, is generating them. This assumption may sometimes lead to rejecting the null hypothesis even when it is true, which defines type 1 error, typically denoted as alpha. Here, alpha is the probability of observing sample means below 48.5 or above 51.5 when the true population mean is 50. Standardizing these probabilities lead to z-values of negative and positive 1.9, with a summed-up cumulative probabilities of 0.0574. This means that if the true mean burning rate of the propellant is 50, there is a 5.74% chance that we will observe a sample mean outside the range of 48.5 to 51.5 generated by such normal distribution, leading us to incorrectly conclude that sample was generated by a normal distribution centered at a mean different from 50. A type 2 error, denoted as beta, occurs when we fail to reject the null hypothesis even though it is false. In other words, we miss detecting that a normal distribution centered at a different value, such as 52, generated the sample and incorrectly conclude the burning rate mean is 50. This figure illustrates the two distributions representing the null and alternative hypotheses. The distribution centered at 50 corresponds to the null hypothesis, while the one centered at 52 represents a potential alternative hypothesis. Our rejection criterion is based on whether the sample mean falls outside the range of 48.5 to 51.5. However, under the alternative hypothesis, it is entirely possible for values between 48.5 and 51.5 to be generated by the normal distribution centered at 52. When this happens, we fail to reject the null hypothesis despite the alternative hypothesis being the main distribution creating the sample. The blue shaded area under the alternative distribution represents the type 2 error, beta. This translates to the probability of our sample mean being between 48.5 and 51.5 when the actual population mean is equal to 52. After standardization, we can see that this probability, which represents beta or type 2 error, is about 0.26. Thank you for watching this video.
See you in the next one.